Hey guys, my name is Hiraku Murakami. I'm back with NovaEdge Academics, and today we'll be going through topic B5, current and circuits. Okay, so first let's talk about electric charge. All right. Well, we know that atoms are made of proton, electron, and neutron, and we know that proton is positive charge and electron has a negative charge. But maybe you've never discussed what that charge is. How much charge do they have, and how we quantify it? Well, first, the electric charge unit is called Coulomb. And we quantify that each proton or electron has 1.6 times 10 power of negative 19 coulomb. We call this the elementary charge. Okay, so each proton, each electron will have this much amount of charge. Okay, this is all in the data booklet. You don't have to memorize, but generally by the end of your 2 years in IB physics, you'll probably have this in your head and you can use it spontaneously. Okay, now one thing to remember is that opposites attract. So if I have positive charge and negative charge close to each other, they're going to attract each other. If I have negative and negative, they're going to repel each other. Or positive and positive, they're going to repel each other. Okay? In electricity, we have two types of electricity. One is static electricity and another is dynamic electricity. So for static, maybe you've come across in your daily life, maybe you're about to touch something, you feel a spark, okay? That's actually static electricity. And the way static electricity works is when two objects that are, either positively or negatively charged come in contact, then that kind of phenomena can happen. But how does that come about? Well, that happens when you have contact with two different objects. So as an example, if I rub this plastic rod with wool, what that does is, well, the wool is actually going to transfer electrons from itself to the rod upon contact. And so the rod becomes negatively charged. And so if you have another rod that's negatively charged, boom, they repel each other. Well, I can have another contrast. So let's say I have negatively charged plastic rod, but I have a glass that's rubbed with silk this time. Well, if I rub glass with silk, what happens actually is the glass transfers electrons to the silk, and so it becomes positively charged. And so always remember that protons do not flow. It's actually the electrons that can flow. They're the ones that are freely moving around, and that's how you can have this kind of process. Okay, but remember that in IB physics we focus on dynamic electricity, so that's what we're going to talk about moving forward. So static electricity, you kind of can forget about it, so focus on dynamic electricity. The first property we're going to talk about in dynamic electricity is current. And what current is just the rate of charge movement, the rate of flow of charge essentially. So Q here is actually the charge. So that's in Coulomb. And T is time, right? So how much charge moves from one spot to the other over time, and that is in seconds. It's crucial that you actually always use seconds. It's never minutes, hours, etc. Okay, and coulomb per second is actually called ampere. So that's the unit for current. So imagine, let's picture this. So imagine this is a wire. This is a copper wire, right? And it's magnified, obviously, right? So let's say I put, 3 electrons to move through the wire and come out here. Okay, each electron has a charge of how many charges? 1.6 times 10 to the 19 coulomb, right? So I need to multiply that by 3. That's the total amount of charge that's flown from point A to point B, right? And I can say, okay, how long did it take? Maybe it took 1 second. So if it took 1 second, then the current is equal to 3 times 10 power of 3 times 1.6 times 10 power of negative 19 over 1 second. Okay, so that's just 4.8 times 10 power of negative 19 ampere. Okay, that's quite low. You're not going to come across that small value of ampere. Okay, let's move on. We have a ton of practice problems, so you're going to know what current is by the end of this. Okay, so let's do another practice problem. So pause the video and give this a try. Alright, so when we say that the current through this is 50 milliampere, we're saying that it transfers 50 times 10 power of negative 3 coulombs per second. That's the rate of flow of charge, okay? So we know the rate. If we know the time, we can actually solve for how much charge in total. So delta Q is equal to I times delta T, which is equal to 50 times 10 power of negative 3 coulomb per second, times it by 1 minute. 1 minute has 60 seconds in it, right? And that becomes 30,000 coulombs. So that's how much times 10 to the power of negative 3 coulomb. So that's how much has transferred over time. Of course, this is just 3 coulombs, okay? Part B, how many electrons flow through the lamp every minute? Well, I know that each electron has 1.6 times 10 to the power of negative 19. So if I divide 3 coulomb by 1.6 times 10 to the power of negative 19 coulomb, I can get 1.875 times 10 to the power of 19 number of electrons, okay? Let's do another practice problem. So pause the video and give this one a try. Okay, so same principle, you have, now you're given the number of electrons and calculate the total charge which flows in that time. So the charge is equal to the number of electrons times the elementary charge. So 2.5 times 10 to the power of 20 times it by 1.6 times 10 to the power of negative 19, which is equal to 40 coulomb, okay? B, determine the electric current. Well, electric current is going to be equal to Q over T. That's 40 coulomb divided by 1 minute. So 1 minute is 60 seconds. Always change to seconds, okay? So that's 2/3. All right? So the second concept that we're going to talk about is called potential difference, okay? And you might actually know this as voltage. Maybe you've taken a class before in high school and you've learned what voltage is, okay? So electrical potential difference is actually the driving force of current. So that's the reason why electrons flow from one place to another. It's not magic. It's because there's some sort of thing that's pushing it to go from there, okay? And that's the electrical potential difference, okay? To better visualize what that is, let me make an analogy with gravity, okay? So in gravity, okay, if I put this ball up on this ramp from here, it's going to actually flow to there, right? So from point A to point B, it's actually going to roll on its own from here to here, right? And that's also not magic either. The reason why that happens is because of gravity. More specifically, it's because there is gravitational potential difference between A and B. And what this means is there's energy level difference between A and B. A has higher gravitational potential or higher gravitational energy than B, which has lower gravitational potential or gravitational energy. So because there's a difference in potential, it flows from A to B, okay? And we actually quantified this before. The work done in moving a ball from A to B is quantified as mg delta h. Delta h is a height difference, right? We've already covered this. This is actually equal to what we call m times by gravitational potential difference. So this G delta H here is actually called gravitational potential difference, okay? This you'll cover more if you're in HO later, but this is how actually it works, okay? And the same principle applies for electrical potential difference. So the reason why, let's say I have a battery, right? I have a battery with certain potential difference or potential voltage. I have 5 volts, for example, 5-volt battery. What's happening is electron is going to flow from one side to the other, from point A to point B, because these two terminals have a certain potential difference. Same way these 2 points have certain potential difference. That's what we call potential difference. So that's the driving force into kicking electron out of the negative terminal and pushing it towards the positive terminal, okay? And we actually quantify voltage as work done per charge, okay? And rearranging this, you're going to see work is equal to Q times V. I hope you see the similarity. Work in gravitation is M times V. G, by the way, here is a subscript, okay? So it's not G like this. It's just a subscript. Here you have work is equal to charge times V. Here you have mass times V, charge times V. So work done in electricity is charge times V, okay? Now, the third concept we're going to explore is electrical resistance, right? And then electrical resistance is a measure of impedance of electrons flow by an object, okay? And the unit is given by ohm here. So it's how much a material resists the flow of electron, okay? And we have this thing called Ohm's law. This is called Ohm's law. You should probably remember that, okay? This is called Ohm's law. It describes the relationship of resistance with voltage over I. And the principle behind electrical resistance is due to its composition. So, you know, in a metal wire, if I zoom in, if I zoom in really, really well, then I'm actually going to see that there's atoms, metallic atoms, because, well, it's a metal wire, so it's made of metallic atoms. It could be copper, it could be anything, right? And these metallic wire, they have a center of the atom called nucleus that's made of protons and neutrons, right? These guys are bigger than electrons, by the way, so they take up a lot of space, right? And so electron is trying to flow from this to this, but there are these guys that are blocking the way. So how much that blocks the way is the resistance, right? Because, well, current is a flow of electron, and each metal type is going to have different, property, right? Some will be closely packed together, maybe some are loosely packed together. So as you can probably guess, if they're closely packed together, they're going to oppose the motion of electron much better, right? So that property, we call it resistivity. Resistivity is the inherent material property that's dependent on their structure. Okay, so higher resistivity means they resist better. Okay, and so resistivity actually is, let me rewrite this actually. R is equal to rho times L over A. So what's that saying? Resistance is equal to the inherent property of the metal times by its length over the cross-sectional area. This is a cross-sectional area. This is the length. Okay, and I hope this makes sense, because if I have a longer wire, right? If I have a longer wire, that means the electron has to go through more of that. So that means resistance goes up. So as length goes up, resistance goes down. But then if I make it wider, like imagine like a pipe, right? If I have a bigger pipe, then it's going to let water flow much better, right? Same way, if I have a bigger area, cross-sectional area, then the resistance is going to go down, okay? And you multiply that by the resistivity. Very important. One more thing I want to talk about is electrical conductivity, which is actually just the inverse of resistivity. And the reason why I'm talking about this is because I'm trying to make a connection between electrical conductivity and thermal conductivity, because we've learned about thermal conductivity before. So if you're not unsure what that is, you can check our previous video. I think it was like topic B2 in thermal transfer. Okay, so we've talked about thermal conductivity before. It's how much the material conducts heat. Electrical conductivity is how much the material conducts electricity. And generally, good electrical conductors are also good thermal conductors. And now I'm actually going to go back and talk why that is. So let's go back to this diagram, okay? So I actually left a note here that temperature also matters. I just forgot to explain why. So, all right, so imagine electrons are trying to get through, right? If the metal wire heats up, okay, if the metal wire heats up, what happens? These guys start vibrating much faster, much rigorously. So it's going to vibrate and vibrate and vibrate and actually block the pathway. It's going to start blocking the pathway. That means resistance goes up. So as temperature goes up, resistance also goes up. Okay, and the reason why is because resistivity is a function of temperature. Okay, so resistance equal to resistivity, which is a function of temperature, times L over A. So as temperature goes up, resistivity goes up. And that's the reason why resistance goes up. Okay, and also to connect it to heat transfer, right? How does heat transfer occur? How does heat get conducted? Well, heat gets conducted because of the vibration of these guys. So when they vibrate, they're going to touch with neighboring atoms and actually conduct the energy, right? So it's going to let energy transfer from one point to another. So that's why these two go hand in hand, okay? Let's do a few practice problems with Ohm's law and the resistivity formula that I've given here. So let's take a problem. Let's take a look at this problem. Pause the video and give this one a try. All right, what voltage is needed to make a current of this pass through this ohmic resistor? V is equal to IR. So let's just multiply those two. 37.8 volts, okay? All right, pause the video and give this one a try. All right, so let's take a look. So we know resistance is equal to this. So the nichrome is right here, right? And they say it's used for electric heaters. And the reason why it's used for electric heaters is because it has a higher resistivity. So look, you can see that this has higher resistivity than this guy, this guy, this guy, and this guy. So it's actually really, really nice. So, all right, so that, let's multiply this times by its length divided by its radius. Well, I need the area, so pi r squared. Pi 0. This. Okay, so put this in your calculator and see if you get the same thing. That should come out to 15.56 ohm, which looks like that. Okay, so pause the video and give this one a try. Okay, so now we're trying to predict the length, so we isolate the length. That's 1.0, 3.4 times 10 to the power of negative 4. Resistivity of aluminum is this, okay? 12.1 kilometer, which is quite long, okay? Now, I'm going to also talk about what resistors are because that's something you need to cover in your IB. Resistors are just the things that have resistance. So they often look like this when you're playing with circuit boards, but anything can be a resistor. It can be like a light bulb. Light bulb is a resistor. It can be a kettle, like kettle. You know how they heat kettle up or heat water up? Is because they have metallic coils in the kettle that they pass current through and heat it up. Okay, and that's why your water gets heated up in a kettle. So that is also a resistor. So anything that has a resistance, a big resistance, is called a resistor. Okay. Last but not least, I'm going to talk about ohmic behavior. Okay, and this is something you need to know conceptually because they will definitely ask you in paper 2, like 1 mark question or paper 1 in multiple choice. So what is ohmic behavior? Well, ohmic behavior is just this relationship. Okay, this relationship of resistance is equal to V over I. You can rearrange it however you want, V equals IR, whatever. But as long as this relationship holds, we say the system behaves in an ohmic way. Okay. However, I said that temperature affects resistance, right? And so why does temperature go up? Well, it's because when your current is high, the resistor gets really hot because there's more electron collisions in the wire, right? So if there's more collisions in the wire, then they heat up the wire, they heat up the protons, which then heats up the wire. So if the current is high, your wire gets hotter and hotter and hotter. That's how the kettle system works, right? And so when it gets hotter and hotter, guess what? Resistance will become hotter as well, okay? And when that happens, this ohmic behavior actually doesn't last. It becomes in a non-ohmic pattern, okay? So a best way to show it is by graph. Let's say I have V versus I. So V is equal to R times I. So you can actually see that that would be the slope, right? So that's the slope. And that's going to behave like this, where the slope is equal to R. That's if ohmic law persists, right? But at higher current, I said that it's going to heat the wire up. So maybe it lasts like this. It acts ohmic till here. But at this point, okay, at this current, the wire gets really, really hot. And if it gets really, really hot, guess what happens? R is going to increase. So the slope is no longer constant. It's going to start increasing. The slope is going to increase. So you can see how the slope here is much lower than slope here because the slope is R. And R now is also increasing as well. So it's no longer constant. This is non-ohmic. Okay? They'll never tell you to calculate stuff non-ohmic, but you have to know this conceptually. All right? Now we're going to stop here. We're going to talk about how circuits work and, series and parallel, as well as ideal ammeter and voltmeter for next video. So stay tuned and see you in that next video. Hey guys, thanks for watching. If you like this kind of video, then consider giving us a like and subscribing to our channel. We have a lot more lecture style video and content like this in our channel, so feel free to go check it out. If you're looking for additional guidances like one-on-one tutors in IB subjects, SAT, TOK essay, IAs, writing, etc., then go to our website at NovaEdgeAcademics.com, fill out the form, and we'll get in touch with us. In the meantime, we'll see you in the next video.